All right, let's do our Inference with Proportions review video 3. So what we're going to do in this one is we've talked about intervals, we've talked about how to change the size of intervals, and so now let's go on to z-tests, okay? And then we'll end with all those assumptions and getting real and what the criteria we need to meet. So here we go. Our one proportion z-test, okay, I've had you do these by hand because I've wanted you to keep in practice of how to do this. So I would have you do your little z-score here. Your p-hat, your sample results, p-hat minus true p, so we're seeing how far away is your sample results from what we expected it to be, okay, over the standard deviation of how varied all those samples are. So p-hat minus the p over the standard deviation of p-hats, okay, which this standard deviation of p-hats formula is that square root of that one that we need to compute ourselves. All right. So then once you get that z-score, okay, to get that p-value, you then compute your norm CDF from that z-score to the other z-score, okay? And so we know if we're going up, you're going to be going from z to positive infinity, and down is going to be the opposite of that. Now, one thing to note if you're doing this by hand, okay, that this is just giving you the area of one tail. Okay, so keep that in mind, because if when you're doing a hypothesis test and your HA, your alternative is asking just is there a significant difference, then it's indicating two tails worth of data. So that means the total p-value would be the value of both of those tails. Okay, so if you were doing this by hand, you would multiply that one p-value by 2 to get the total p-value. All right, now if you did that in your calculator, which would be done with the stat over to test, if you happened to do the number 5 one proportion z-test by hand, and you could do that. Make sure if you were putting in your x values that you were putting in those as whole numbers again, okay? But if you had a two-tailed test on this one, then the calculator already does the combining of both tails together when it gives you an answer, okay? So calculator does the doubling for you. You don't need to then double it. All right, so let's take a look at that two proportion z-test calculating. And then then we talk about the conclusions. Okay. So for the two proportion tests, I've not ever made you do this by hand. We've looked at some things to recognize the formula for those, just if it was a multiple choice question. But for us, we've always computed them with our calculator. And so we've always used this two proportion z-test. And again, these are for two separate independent samples. Again, making sure, okay, that if they say 13% of 27, okay, you don't put 0.13 in here, and you don't put whatever 0.13 times 27 is. You need to round it to a whole number there, okay? And then you put all your data in and compute. You will then get your p-value and your z-score and your test statistic and your p-value. So we know if your p-value is low, reject HO. So if our p-value is low, we're going to reject HO. And then your next sentence is about HA. So I'm rejecting HO. So I have evidence that I have evidence to support HA's as an assumption, hypothesis, okay? All right, but hey, if your p-value is not low, then what that tells me is your data was not very rare. It was, just probably because of sampling variability. If your p-value is larger, then it's probably just because of sampling variability. I would fail to reject, so I would not then go and support HA. Do not ever say something like HO is true or there is evidence to suggest HO is true. Oh, no, no. Oh, no, no. Okay? We do not have evidence of HO. Evidence is always about HA. All right. Now let's take a look at this connection between if we did something with interval and test, and then that we looked at those results and kind of tried to see if they jive together. So with one proportion, think about this. If we reject HO, okay, then we would not, we wouldn't see that claimed value in our interval, okay? That claimed value, that HO, was rejected. So that would mean it's not in the interval. That would be something like this. If we are claiming that a proportion is 0.23 and we get a p-value that rejects it, well, our interval might be something like this. It's going to be completely above or completely below the 0.23, 32 to 45 or whatever. Okay, completely above or below. All right. But what if we fail to reject HO? We don't have evidence to get rid of it. So then you would probably have something where HO is in the interval. So if we had that again, our null hypothesis of that, our interval might be something like this: 0.18 to 0.25. See? And that HO is in there. Okay. So that could happen there. And we do not have evidence of that to support HA. Now, remember this, whenever we are doing stuff for a test for two proportions, okay, then let's talk about what's happening with that. We end up doing something, we're making our interval like this. We're saying, okay, I'm subtracting, and then here's the interval that I get, okay? And so remember that interval I get it's evidence about there being a difference between those two proportions. So we're always talking, so if this is completely above 0, then you have evidence of a significant difference, okay? If 0 is in there, then you don't have evidence of a clear, significant difference occurring, okay? So rejecting the null would say, I got significant difference. 0 is not in there because I have evidence of a significant difference, okay? And then, of course, failing to reject the null, then I've got, not big deal happening. I got 0 in that interval because nothing major is happening. I do not have evidence that there's a big difference between those two speculated proportions, okay? All right, assumptions. Here we go. Going to get real. Okay, remember that we are saying randomly selected number of subjects, use context, randomly selected number of students, or whatever. But if you have an experiment, you are not saying randomly selected subjects. You are saying I'm saying that these however many subjects were randomly assigned to their treatment groups, whether that's the placebo or the other treatment, okay? And so we're doing that in both cases, whether you have one proportion tester interval or two proportion tester interval. Two, you're just saying it for both of them. You're saying these 13 men, these 19 women, or whatever that number is, and they are being randomly assigned or they were randomly selected subjects. Okay? Now, let's take a look at our independent. Independent, N is less than 10% of the population. So N is our number of subjects, is less than 10% of all such students that this professor has. Something along the lines of that. So using that context. And when we have those two proportions, we're doing that same thing again. N is less than 10% of the population of all such subjects, and so on and so forth. But again, for two, we're having to say that the subjects in this one group are independent of the subjects in the other group, okay, because we don't want to have them double counted. All right, are large enough. So let's review this because when we come into this review, we've been doing means for a while. So let's recall that for proportions, are large enough is not greater than or equal to 30. It is that we have to have at least 10 successes and at least 10 failures. So that's going to be n times your p greater than or equal to 10, and n times your 1 minus p greater than or equal to 10. Okay, so that's your number of successes and number of failures. And of course, if you're doing intervals and you don't have your p, you have p hat there. Okay. But look over here, just make sure that when you have two separate proportions, we have to make sure we're doing this for both samples. Our first set of data, at least 10 successes and failures, and our second set of data, at least 10 successes and failures. Okay, and then upon those happening, we got the approximately normal model applying. Okay, I did have this little special note here. Just remember that the best it can be is if you use true P. And so I'm referencing this little, section here and such. But if you don't have that, you can just use P hat. The worst case scenario is those don't jive. Please don't cry. Just use 0.5. Okay. So that is it. And it again ends with your approximately normal model applies. So then we can do our Z, our normal model math. Okay.